Okay, so now we're going to move on to the notion of expectation in quantum mechanics, more of the expectation value, and how this can be used to determine measurements, and how we can perform measurements by using this expectation value. So, from normal statistics, we know that the expected value is the sum or integral of the probability distribution of outcomes multiplied by the value of the outcome it takes on. I.e., let's say, in the discrete case, expectation value of some value here is just a sum where I goes from 1 to n of, let's say, x p of x, pi of x. Okay, this is known as your expectation value, also written as this there, as so. Okay, so it's known as the sum or the integral of the probability of distributions of outcomes multiplied by the value of the outcome it takes on, or the average value of the random variable in shorter terms. Okay. However, in quantum mechanics, this is not the case. So, QM, expectation value is different than the interpretation in regular statistics. Okay, now the reason for this is, if we make an initial measurement on a system, by the Copenhagen interpretation, the wave function collapses to the value obtained, and if rapid measurements are made, then the result will simply be repeated. As we said before, the wave function won't have enough time. If we take the time interval to be short enough, we won't have enough time to spread out. So if we do repeated measurements in successive intervals where the time interval is small enough, then we'll get the repeated result. Okay, rather this value, this expected value, we'll use just x, let's say for position, is the average of the measurements on particles. Okay, all in the state psi. So this expected value is the average of measurements on particles all in the state psi. Okay, you must either return the particle to its original state, which sounds quite hard. You know, after you've done this initial measurement, you must somehow return it back to its initial state and then repeat the measurement again and again and again. Do this all in this successive time, but very, very small intervals. Or you prepare loads of systems, maybe like a row of systems, and you make measurements, successive measurements on each of these, each in the same state. You essentially make an ensemble of particles, all in the state psi. And the expected value is the average of the repeated measurements on this ensemble of identical particles, not on one and the same system. Okay, so say, I don't know, maybe a little diagram could be like, let's say you have little particles in a row like so. You take measurements on each of these particles here, and that will be your average measurement once you find all of these. Okay. So it's not taking it on one and then, bringing it back to its original state and doing it again. You've changed it once you measure it. You've changed the actual wave function itself. So this is sort of the way we have to do it. Okay. So we have time dependence of the wave function, and we'll see that the time dependence of this will mean that this will be changing. Okay, so the expected value will change. So expected value of x will change due to the time dependence of psi, right? And we'll just do this by just taking the derivative of it, okay? So remember, explicitly, this in integral form on the wave function is just this product right here. Okay. So if I wanted to take the time derivative of this, again, the time derivative is just going to go within the integral itself. We'll get something of this form. I put the x out here because x has no time dependence. But we know that the wave function itself does. Okay, so now we have to break this up. So we'll break up the modulus that we have here, and we'll end up with, as before actually, when we did the whole time derivative of the norm of the wave function, the probability density, it's almost exactly the same. Except for now, we're going to have this value on the outside. So for the first few steps, it's pretty much just trivial if we just look back. So we'll be ending up with this form. So we have the x, and then we end up with this point here. And this is where it deviates slightly. Okay, so all we've done is we've invoked the Schrödinger equation after taking the time derivatives of the wave function. So we end up with this right here. And now, if we use the product rule, we can put this x within this part here and pull out the whole entire derivative. Okay, so I know that if I did the entire derivative of this, i.e. x multiplied by conjugate of psi, the spatial derivative, take away this, I'll be left with, by integration by parts, that is, take away d psi conjugate by dx psi plus psi d psi, take away d psi conjugate by dx psi. Okay, so I can rearrange this to make this fit up here and then just plug that straight in. Okay, so what I'm actually left with after doing this, and you could say it's integration by parts. It really is, but I've just invoked the product rule by spotting what's within the integral. So we put this back into our integral, and we end up with this. So d by dx of everything in here dx, take away the integral minus infinity to plus infinity of psi d psi by dx, take away d psi conjugate by dx psi, all dx. Okay, now what we can see here is this is going to be 0 because we have the derivative of the integral and we know that this is just going to be evaluated at the boundary points. And what did we have before? We had that the wave function at the boundaries of plus and minus infinity, they vanish. So this entire first part is going to disappear. So all this is going to be equal to is just minus I h bar over 2m, and then the integral from minus infinity to positive infinity of this product right here. Okay. So, if we then again use integration by parts, or the exact same sort of reasoning I did up here to put the x value back into this second term right here, then we're going to be left with the time derivative of the expectation value is equal to minus I h bar over 2m with the integral from minus infinity to plus infinity of psi d psi by dx. Take away d by dx plus psi conjugate d psi by dx. And all of this is the integrand. What I did here actually was I picked one of these terms and I performed integration by parts on one of them. I said that, let's say I pick the right hand term, this term right here. I said that this is just equal to total derivative d by dx, which means that this should not be a partial. Oh no, it could be, yeah, it could be. In which case this is not definite, it's a partial. We'll rewrite that. So it's partial d by dx of psi with its conjugate is equal to d psi by dx psi plus psi conjugate d psi by dx. And then again, just move one term to the other to get this this term, and then afterwards you end up with this. So you put that into a little box down here so we don't mess this up. So what are we left with? Well, we're left with this boundary term here. So we just have like so, minus infinity to plus infinity, and then we have minus I h bar over m, sorry, because these two add together the same term, multiplied by the integral of psi conjugate multiplied by d psi by dx. Okay. So we're left with this result here, and this is going to vanish to 0. So finally, we have that the time derivative of the expectation value is minus I h bar over m multiplied by the integral of psi d psi by dx. Okay, and this is essentially sort of the velocity of the expectation value. So this is the time derivative, right? So since quantum mechanics does not permit a solid meaning for velocity stemming from the non-determinate position, there's no clear definition on a velocity in quantum mechanics. So we'll use this as to make a postulate that this is the average velocity in a way. We could say the expected velocity is equal to this right here. Okay. So what else could we compute with this? Well, we could try and compute the average momentum, or the expected momentum, expected value for momentum, which is just this multiplied by m, or m d by dx by dt. Okay. So what we have here is a few. Well, we'll have the position for the expected position value, which is just given by this. And we can write that the momentum is just the integral of the wave function with p as so. Actually, no, that's wrong. It's equal to this, but multiplied by m. So it's equal to minus IH bar d psi d by dx of psi of x. Since the momentum is just this time derivative of the expectation value multiplied by the mass. So if we pull the factor of minus IH bar in, we have this. Okay, so if we treat these as operators, if we treat x and p both as operators acting on the wave function psi, which must be put in between the product of the two. If you don't put it in between, what do you get? You get the norm, and then you just get the value on the outside. But since psi depends on x and t, it's better to put these in between before you do the normalization. Okay, otherwise you just get nothing really. Nothing really happens. Okay, so you put it in between the product of the conjugate of psi and psi, and these both act on the wave function psi. All such quantities can be written in terms of x and p. Okay, so all dynamic quantities that we want can be written in x in terms of x and p. For example, the kinetic energy is given by p squared over 2m, right? So for any operator depending on x and p, I'll say for any operator of functions x and p, I'll say q of x and p, then the expectation value is given by just the integral of complex conjugate of the wave function with this operator here in the middle, multiplied by just the wave function dx. Okay, or more explicitly, if we wanted it in just terms of x, q of x minus IH bar d by dx psi dx. Okay. For example, we could do the kinetic energy as given above. We can say that the expectation value for this kinetic energy, I'm going to call it T here, is just given by minus h bar squared over 2m. This is by substituting the p squared over 2m right here in the middle. And then we have the integral of psi as so. Okay, so this is the notion of the expectation value and how we can start to perform measurements in quantum mechanics. You can see it's clearly different than what we do in classical mechanics, and it all stems from the non-determinacy of having a position, non-determinacy of velocity, and since the dynamic variables can come from position and essentially momentum, which momentum does depend on the velocity, you have to approach it in this sort of way. All right, thank you.